Hello everyone, welcome to Chapter 3 Electrochemistry. In this video, we are going to talk about Chapter 3.3 Electrolytic Cell. So by the end of the lessons, you should be able to draw an electrolytic cell and describe the operations of the cell, explain the influence of the following factors on the selective discharge of a species at the electrode. So we have the factor of SRP value, concentrations of a species, and the nature of electrode. Next, we want to predict electrolysis of the following electrolyte using inert electrodes. We have molten salt, water, concentrated and dilute aqueous NaCl, and aqueous sodium sulfate solution. Predict the product of electrolysis using an appropriate examples. State Faraday's law of electrolysis and using this law in calculation. And lastly, to set up electrolytic cell and determine Faraday constant. Alright, so for an electrolytic cell, it is an electrochemical cell that undergoes a redox reactions when electrical energy is supplied. So it refers to a non-spontaneous reaction which requires supply of electrical energy. Usually we will use battery as the source of energy. So it converts electrical energy into chemical energy, okay, to push a reactions to occur. So reactions that occur in this electrolytic cell, the process is known as the electrolysis. So in this electrolytic cell, it consists of only one beaker containing one electrolyte. Still, we are having two electrodes, which is the anode, oxidations occur, and cathode, reductions occur. And an important thing is battery, so source of a power supply. You have your connecting wires and emitters to measure the current flow. So the setup of electrolytic cell look like this. So we still have our anode positive terminal, and then we have our cathode, which is the negative terminal. We only containing one beaker with one electrolyte. Okay, with two electrodes over here. So you can notice over here in this setup of apparatus, we have the source of battery, okay, electrical energy. So at anode, oxidations occur. So it releases the electron. It will flow via the battery and then towards cathode. So the electron will be gained through this reductions process. So this is a simple diagram represent electrolytic cell. So our electrode, it acts as a circuit connector. It acts as a site for precipitations to occur. As you can look at this diagram here, cation is attracted towards cathode, and then anion is attracted towards anode. Okay, so we will expect some precipitations to occur. So this electrode, usually we are using inert or inactive electrode. So for example, platinum or graphite. So graphite is carbon. Okay, so inert electrodes are often used as they do not react with the electrolyte. So we only generate the product from the electrolyte itself. The second term over here, electrolytes, which is a liquid that conduct electricity due to the presence of positive and negative ions. So it must be in molten state or aqueous state so that we consist of this ion which can move freely. Okay, only you have free electrons, free moving electrons, it is able to conduct electricity. Okay, so in this example, sodium chloride in molten state, we have the liquid phase. Okay, and then sodium chloride in aqueous phase, sodium sulfate in aqueous phase. So these are the example. Alright, so next let's look at the operations of an electrolytic cell. So a direct current sources supply electricity to force reactions to occur. As I mentioned just now, we must use some energy to push the reaction. Okay, so negative ion attract to the positive terminal anode in which oxidations occur. So this is a process of losing electrons. And at the same time, the positive ion will attract to the negative terminal, and reductions occur. So the electrons from anode will be gained by the species at cathode here. Okay, so ions are said to be discharged at the electrode. Discharge, it means that it refers to the oxidations and reductions process. So what product you will get at these electrodes. So let's look at the differences between galvanic cell and electrolytic cell. So as we learned in chapter 3.1 and 3.2 earlier, in galvanic cell, we know that it is a spontaneous reactions in which we don't have to use battery. Okay, it is a spontaneous reactions. Also, for galvanic cell, electron is generated at anode. So anode for this galvanic cell is a negative terminal. Still, we have oxidation process. Okay, electron is consumed at cathode, positive terminal. So electrons flow from anode to cathode. So from oxidation process to reduction process. But now, look at this electrolytic cell. Okay, we need to use electrical energy to drive a non-spontaneous reactions to occur. So difference from galvanics, electrolytic cell is non-spontaneous reaction. That is the reason why we need to use battery. Okay, and then pay attention over here. Electron is removed from anode, but for electrolytic cell, we have this positive terminal. Okay, for cathode, it is a negative terminal. Okay, similar as the galvanic cell, electrons still flow from anode to cathode. They are just changing the terminals only. So for galvanic, negative to positive. For electrolytic, from positive to negative. Alright, so if you want to refer back to the simple diagrams over here, anode is the positive terminal, and it is closer to this battery, the positive side at this battery. And the cathode negative terminal is closer to the negative side of this battery. Next, let's look at the factors affecting the product of electrolysis. So it refers to selective discharge of a species. So the word selective refers to if you got two choices, which one we want to choose for a species to undergo either oxidations or reduction. So first factors is based on SRP values. So standard reductions potential. So you need to refer to that SRP table. So when two half reactions are possible at electrode, for anode, we want oxidations to occur. For cathode, reductions occur. So anode oxidations occur, we will select the species which have a more negative electropotentials value, whereas reactions prefer species which will have a more positive electropotentials value. The second factor is based on concentrations of a species, but these concentrations, it will only affect the discharge of anion chloride only. Okay, only affect chloride ion, Cl minus. The chloride ion, which will have a higher concentrations, are preferable to be oxidized. Okay, this is only at anode. You can jot down over here, only at anode. So chloride with higher concentrations will be discharged. And the third factor is the nature of electrodes. So we know that the electrodes is classified into two types. The first one is inert electrodes. So the examples of inert electrodes, we have graphite, which is carbon, and platinum. So these two electrodes are normally used in electrolysis. Okay, inert electrodes do not involve in a reaction. The second type of electrode is active electrode. So the words active itself means that it will involve in this electrolysis process. So this metal electrode will dissolve to form metallic ion. So for example, copper becomes copper 2+, silver becomes Ag+. So in this case, electrolyte usually will contain the ion of the same metal. So given the examples, copper electrode dissolved to form Cu2+ ion. So for electrolysis, it refers to a chemical process that uses electricity for a non-spontaneous redox reactions to occur. So this happens at an electrolytic cell. The question is, how are we going to determine which species to be discharged? So the word discharge means which species will undergo oxidations at anode or reductions at cathode. You need to be able to predict the observation and the product at both terminals. So here are some guidelines for you. If there are two species present overall, and these two species, one of it is the water, we need to identify the movement of ion towards anode and cathode. So of course, for this H2O, it is neutral. So H2O can move to anode as well as cathode. Okay, remember that the anode is our positive terminal in electrolytic cell. So an anode, okay, water undergoes oxidations to produce oxygen gas. So remember, water, oxidations, oxygen gas. So based on the SRP table, the E naught value, your standard reduction potential, is positive 1.23 volt. Okay, so refer to your SRP table, you will see. Okay, so in this case, we focus water. Okay, it will undergo oxidation, so we reverse the reactions, and you can see oxygen gas produced. So the values positive 1.23 is what we use to compare. Okay, we will use these values for comparison. Okay, so you jot down first the equations and the E naught value. So if H2O and other anion present at the same time, choose the species which has a more negative SRP value. So for example, if I compare between the water and maybe bromine, in this case bromine, okay, bromine has a more negative SRP value. So bromine will be discharged. So this is an example for you. Comparing between anion and water. So if let's say you comparing between bromine with water, iodine with water, concentrated chloride ion with water, so this species will be selected. So put a tick over here. Okay, they will be oxidized because they have a more negative SRP value than water. And for the, if let's say you have this anion comparing with water, so for example, fluoride ion, diluted Cl minus, they will never be oxidized. Okay, because F minus has a more positive value. We don't want that one. And then Cl minus is because of the factors of concentration. So we don't choose diluted Cl minus. We choose H2O instead. Okay, another one is over here, oxo anion. So for example, sulfide ion, SO42 minus, NO3 minus, PO43 minus. So this oxo anion will also never be oxidized. Okay, because the central atoms, sulfur, nitrogen, phosphorus, they are already at the highest oxidizing state. So they cannot be further oxidized again. So if it's happened at cathode, we know that cathode reductions will occur. Okay, so focus on the water first. Water will undergo reductions to produce hydrogen gas. Okay, focus over here, water, reduction, hydrogen gas. So based on your SRP table, we have the E naught value equals negative 0.83 volt. So you can look over here, water undergo reduction to produce hydrogen gas. The rest of it is just to balance up the equation. So the value negative 0.83, we're going to use this value to compare with another cation. Okay, so copy this one down and take note on the value here. So if let's say in an electrolyte, or you consist of H2O with another cation present. Cation is a positively charged ion which will attract to this negative terminal. So we are going to choose between two of these species, which one having a more positive SRP value. We choose the one with more positive SRP value. So looking at this summary table, if you compare between the metal cation and water, cation of a less reactive metal, okay, will be chosen. For example, if you got copper CO2 plus, Ag plus, Zn2 plus, Au3 plus, nickel, and chromium, they will be reduced because they have a more positive SRP value than water. And if it's a cation of a reactive metal, lithium, Li plus, Na plus, K plus, Ba2 plus, A2 plus, they have a lower value of SRP. So this cation will never be reduced because of their less positive or more negative SRP value. Okay, so there is a yes, yes, and a no, no here. Alright, so let's using this example, we have silver nitrate aqueous solutions using inert electrode. Okay, so inert electrode either is platinum, PT, or graphite. So the species that present inside the electrolyte of silver nitrate consists of Ag plus and NO3 minus. And because this is an aqueous solution, so the water H2O molecule must be there. Okay, must present. So maybe you can draw a simple diagrams over here in which I have anode on the left and then cathode on the right. So anode is my positive terminal and cathode is my negative terminal. So anion will move towards anode. So in this case, I have NO3 at anode and also H2O at anode. Okay, and then the cathode side, I have a cation, which is Ag plus, and the neutral water molecule. Okay, so let's fill in the blanks over here. During electrolysis, okay, the species will move towards anode. So anion move towards anode. So in this electrolyte, the NO3 minus, your nitrate ion, and water will move towards anode. So between two of these species, NO3 minus will not be oxidized because it is an oxoanion. So oxoanion means that the central atom nitrogen, in this case, is at its highest oxidation state. Okay, so it won't be oxidized. So we are going to choose H2O to be oxidized at anode. Okay, H2O oxidized at anode to produce oxygen gas. Okay, so at the cathode side, silver ion and water will move towards cathode. So cation move toward cathode, neutral molecule also move to cathode. But Ag plus is chosen to undergo reduction as it has a more positive E naught value. Okay, cathode prefer a more positive E naught value. So this is an interpretation. So which species we're going to choose at each terminal. Then you have to write out its half equation, predict the product, and predict the observation. So for anode, since we choose H2O to be discharged, so H2O undergoes oxidations to produce oxygen gas. So the product form over here is oxygen gas. The observation is what you can see. We can observe some gas bubble release. At cathode, silver Ag plus will undergo reductions to generate or to produce silver solid. So this is the precipitate. So the product forms over here, you can see a silver solid. Okay, silver solid. And observation, what can you see? What is the color? Silver solid deposited. So silver itself means the colors already. And then you are having this overall equations. So just add up both of this. But don't forget that for cathode, okay, the one for silver, we need to multiply with 4. So the number of electron will be the same. And then you just cancel off only. Alright, so the next example given here is a potassium fluoride aqueous solution using inert electrode. Okay, so we need to identify what is the species present. So in KF aqueous solutions, we have a potassium ion, we have fluoride ion, as well as H2O molecule. So you can use this simple diagram. Anode means refers to positive terminal. So anion move towards anode. So we have this F minus and also H2O. You can choose between these two. Okay, and then for cathode side, negative terminal, cation attract to cathode. So for potassium ion and also H2O, we need to interpret which one to choose. So during this electrolysis, fluoride ion and water will move towards anodes. Okay, but H2O will be oxidized due to the more negative SRP value. You may refer to this summary table. So fluoride ions will not be chosen if it comparing with H2O. Okay, so H2O will be oxidized due to its more negative SRP value. So at the cathode side, we have the potassium ion and water will move towards cathode. And water is chosen to undergo reductions as it has a more positive E naught value. Okay, so for this half equations for anode, water undergoes oxidation to produce oxygen gas. So remember, anode oxidations, oxygen gas. So product form is oxygen gas. Observations will be gas bubble or release, gas bubble or evolve. For cathode, still we are using water, but cathode, we have this reductions process. So water will undergo reductions to produce H2 gas. Okay, so the product form is the hydrogen gas, and still we are observing some gas bubble evolve. Don't forget that for cathode side, you need to make sure the number of electrons are the same. So you can either multiply this equation, the reduction equations, by 2, or you divide the first equations by half. So either way will do, and you will get the overall equations like this. 2H2O liquid into 1 mole of oxygen with 2 mole of hydrogen gas.